So we'd already started talking about hypothesis testing. This is kind of the great white whale here of statistics, if you like a good literary reference. This is what statistics is all about. We have learned pretty much everything we have to come up to this point, pretty much, or at least it's one of the best things. Now, remember, we talked last week, we talked about you always have to declare a null and an alternative hypothesis. A null and alternative hypothesis, H naught, H0, and H1. And these are the three types that we will concern ourselves with. The two-tailed test, the left-tailed test, the right-tailed test. The only two parameters we're going to be testing in this course are the population proportion and the population mean. Those are the only two we're going to concern ourselves with. So there's only so many decisions we're going to make. There's four possibilities. Your null hypothesis, in reality, whether you can know it or not truly, in reality, your null hypothesis is either true or false. Whatever you're assuming is null, whatever you're assuming for the status quo, is either true or false. Now, what will happen is when the null hypothesis is actually true, but you draw the conclusion to reject the null hypothesis. This is called a type 1 error. It's a mistake because you are throwing out a null hypothesis by mistake when you should not have thrown it out because it actually is true. So these are the only two. So this is the reality, but again, reality isn't something you can always know for certain. These are the only conclusions you'll draw in a hypothesis test. You will either reject the null hypothesis, or you will not reject the null hypothesis because you lack the evidence to do so. Notice how we don't say reject H naught and accept H naught. We never say that we accept H naught. We just say that in this particular example, we don't have enough evidence to reject it like we usually want to. So just keep that in mind. Now, next up, you can reject H naught, that's the decision you draw, when in fact H naught really is false. The null hypothesis is actually false. So if you reject something that is false, you've made the correct decision. So correct decision. And that's a good thing. That's not an error. I'm going to put this in red. No. Come on. Now the next box here, it says do not reject H naught when in fact H naught is true. That is a correct decision. If H naught is true, if the null hypothesis is actually honest to goodness true, we would not want to reject it. And in this particular box, we have made the correct decision. Finally, if we fail to reject H naught, we don't reject it, and actually H naught is false. If it's false, we should have rejected it. So if we're not rejecting it, we've made an error. In fact, we're making something called a type 2 error. So this is a useful little box. There's two states of nature, two states of reality, and then there's two conclusions you'll draw. You don't know, the problem is you can't ever know if you're right. You go out there, you collect research, you're looking at the research, but there's always a possibility that you're wrong. There's always a probability, in fact, that you're wrong. In fact, we're going to set the level of a test which we call alpha, we're going to call that the probability of making a type 1 error, and that's something that we get to determine before the fact. Now, look at what all this says at the top. There's 4 outcomes. You reject the null hypothesis when you should not have, or rather when you should have. You don't reject the null hypothesis when it is true, so good job. But basically, you incorrectly reject H naught, or you incorrectly basically accept it. So those are the 4 states of nature. This is similar to a criminal trial. This is a great example. Let's say, so in a criminal trial, you have a defendant, someone who is being charged with a crime, and now we're going to trial to determine whether or not the person's guilty or innocent, and whether or not we're going to, put them in jail, what their sentence will be, community service, whatever. There's 2 states of reality. There's 2 states of reality. The defendant can be innocent. The defendant can be innocent, so the defendant truly, in reality, did not commit the crime they're being charged with. But a guilty verdict is still rendered. This is a mistake or an error. But that happens all the time, right? We hear about 20 years later, someone who spent the last 20 years in prison, suddenly there's new evidence that comes out that proves that they were actually innocent. They were not. They did not commit that crime, and we have made a mistake as a society. We owe them something. We obviously need to release them immediately from prison, and generally they will sue, and a lot of the times they'll win. So that does happen, and that's a mistake. Now, in the case that the defendant truly is guilty, truly did commit the crime that we're talking about, and a guilty verdict is rendered, that is a correct decision. Whether or not we know 100% it's a correct decision is not always going to happen, but it's still correct. Now, in the case that the defendant is innocent and we make a not guilty verdict, again, correct decision. Notice the big key here is that we either render a guilty verdict or the court renders a not guilty verdict. The court does not say you're either guilty or innocent. The court says you're either guilty or not guilty. All that not guilty means in a court is that we just don't have enough evidence, enough proof to convict the person and say that they were guilty. That's all the not guilty verdict means. And then, of course, finally, if the defendant is guilty, but we render a not guilty verdict, we've made a mistake. That is the incorrect decision to make there. But it's because we don't have the evidence to convict them. We're not going to put someone in jail if we're not, we think we're sure that they committed the crime. Now, I know that the justice system doesn't always work out like that. And I know there's a lot of horrible cases in history in every country, not just the United States, of the justice system being completely corrupt. So we're not talking about those, but those would fall into the mistakes. And that usually happens where an innocent person is thrown into jail nonetheless. Really sad when that happens, but unfortunately it does happen. So again, there's 2 outcomes to a hypothesis test. We either reject the null hypothesis, or we fail to reject, or we do not reject the null hypothesis. We never accept the null hypothesis. There's a couple reasons why that this is established like this, but you don't just accept it, because if you accept the null hypothesis, you're saying, oh well, the book is closed on it. The status quo is just forever upheld. But in reality, it's more fun to try and challenge the status quo, which is what the null hypothesis represents. Again, there's some advanced level reasoning for why that we don't necessarily need to go into at this moment. It wouldn't help you or anything. So we either reject the null hypothesis or we don't reject it. Now we use two lowercase Greek symbols, alpha and beta. That's not a B, that's a beta. That's not an A, that's an alpha. We're going to say that alpha is the probability of a type 1 error. Thus, alpha is the probability of rejecting the null hypothesis when the null hypothesis is true. That is something that we get to decide. We get to determine alpha. In fact, we call it the level of significance for the test. The most common level of significance is 0.05, though you can use 0.01, you can use 0.10. You can actually use any number between 0 and 1. It's a probability, so you can use any probability, but you want it to be small, but the irony is you don't want it to be too small. And that's because whether or not we reject the null hypothesis depends entirely on alpha. Next up, you have beta, and that's the probability of a type 2 error. Thus, it's the probability of failing to reject the null hypothesis when you actually should have, because the alternative is true. So some interesting ideas to this construction. This construction actually stems a lot from Greek philosophy, from Plato and Aristotle and the like. When it comes to the idea of rejecting or supporting a claim or something along those lines, very important. It's a subfield of philosophy called phenomenology, like studying phenomena and things like that. But again, we don't need to go too deep into it. So the level of significance, alpha, is the probability of making a type 1 error. It is something that we decide. The probability of making a type 1 error, alpha, is chosen by the researcher before the sample data is collected. It's chosen by the researcher at the beginning when they're setting up the hypothesis test and planning it out and then going to execute. That's kind of interesting. We set the probability that we make a mistake. Yes. And again, it's kind of hard to explain why completely. The reason is what we're doing is we are setting a threshold that we are comfortable with before completing the hypothesis test, where we say, okay, we are picking a probability of making this type of error before the fact, and that's as low as we're willing to go, or as high as you're willing to go. This is as much error as we're willing to take on whenever we run this hypothesis test. The most common levels of alpha of significance are 0.05, 0.01, and 0.10. To be honest, we're not going to explore a type 2 error all that much in this course. We define it, and then we can talk about what the wording would be. So let's look at these. For each of the following claims, explain what it would mean to make a type 1 error. What would it mean to make a type 2 error? Well, we should actually then write out what the null and alternative hypotheses would be. In 2008, 62% of Americans regularly volunteered their time for charity work. A researcher believes that this percentage is different today. So the null hypothesis, which is always going to be a statement of equality, is going to be that P, the proportion of American adults who regularly volunteer their time for charity work, is equal to 0.62 or 62%. The researcher believes that the percentage is different today. So then the alternative hypothesis is that P is different from 0.62, is not in fact 0.62. But now we can do something interesting. A type 1 error, which is rejecting the null hypothesis when in fact it is true. This then would be, and again, it's going to be a little bit verbose. We're going to have to use some big words to say it. This is going to be rejecting the fact that 62% of Americans still volunteer for charity work, when in reality, that's false. In reality, some number other than 62% volunteer for charity work. So if we make a type 1 error in this setup, we are claiming that there's enough evidence to support the alternative hypothesis, the idea that no, it's not 62%. However, in reality, it actually is 62%. That's what a type 1 error would be in this case. A type 2 error which is the error of failing to reject H naught when in fact it is false. This is going to be where we conclude that there is not enough evidence to reject the idea that 62% of Americans today still volunteer for charity work, when in fact it really is not 62% anymore. This would be us, this would be kind of like we're claiming that the alternative hypothesis is the case, even though that's technically not what we do. This is us claiming that the null hypothesis may very well be the case, when in fact the null hypothesis is no longer true in this particular case. We'll look at one more example here. According to a study published in March 2006, the average length of a phone call on a cell phone was 3.25 minutes. A researcher believes the mean length of the call has increased since then. So here, H naught would be that the mean length, mu, is 3.25 minutes. The alternative hypothesis, H1, is that the mean length is now greater than 3.25 minutes. A type 1 error here would be that the mean, rejecting the null hypothesis when in fact it is true. So type 1 error would be if we say actually the mean length of a phone call is now greater than 3.25 minutes, when in fact it's not, it's still equal to 3.25 minutes. That would be the mistake we make, where we support the alternative hypothesis even though the null hypothesis is the one that's actually true. And then a type 2 error here would be whenever we say we fail to reject the null hypothesis when in fact it's false. This would be us saying, well, we don't have enough evidence to support the idea that the null hypothesis is greater than 3.25, that the average call length is greater than 3.25, when in actuality it is greater than 3.25. So, and that's what making the errors would be there. So whenever we are drawing conclusions to hypothesis testing, you're going to word it where you're either rejecting the null hypothesis in favor of the alternative, or you're not doing that. So According to a study published, the mean length of a cell phone call, 3.25 minutes. A researcher believes the mean length of the call has increased, so the alternative hypothesis is that the mean length of a phone call has increased. So we go out there, we collect the sample evidence, and it indicates that the null hypothesis should be rejected. The conclusion then that we'd state is this. If we're rejecting the null hypothesis, we're saying there is sufficient evidence to conclude that the mean length of a phone call on a cell phone is greater than 3.25 minutes. That's how we word it. It's a little strange, admittedly, but that is how we word it. If you're rejecting the null hypothesis, you're saying you have sufficient evidence from the sample to support the alternative hypothesis. What if, in actuality, the sample indicates that the null hypothesis should not be rejected? The way we word that conclusion, we say there is not sufficient evidence to conclude that the mean length of a phone call is greater than 3.25 minutes. We don't have enough evidence to support the alternative hypothesis. So kind of an interesting idea here, hypothesis testing. Moving on to the next section. I told you there's only going to be two parameters that we're going to test in this course. The population proportion, which we're going to handle today, and then the population mean or average, which we will handle next time. There's going to be three ways to test the hypothesis. You can use the classical approach, which we will look at. Kind of the better way, in my opinion, is something called the p-value approach. The p-value is going to be a calculation we make after we collect our sample evidence. That is the probability of making a type 1 error. That is, the p-value will be, well, not quite. It's a little bit different than that. Because alpha is the probability of making a type 1 error. So the p-value is going to be kind of a weird probability we're going to calculate. And most people will say it's not even a probability, but it actually is. The third way is to do a confidence interval, which we will maybe have a chance to look at. So let's look at the classical approach to calculating this hypothesis test, to actually running the hypothesis test and determining what your conclusion is going to be. So first and foremost, you always need to declare your null and alternative hypotheses. If you're running a two-tailed test, the null hypothesis is that the true population proportion is equal to some assumed value. So whatever value you're testing, this part will be very clear how to set this up. Excuse me. The alternative hypothesis will be that your proportion is not equal. Then you have your left-tailed test, which is that the alternative is that the true proportion is less than some value, and the right-tailed test, which is the alternative says that the proportion is greater than some value. So your first step is to set up your hypotheses, what they are, determine what they should be. You really have to do that at the beginning because that's going to tell you what to do with the rest of the hypothesis test. Next up, you select a level of significance, alpha, based on the seriousness or based on how important it is you know of making a type 1 error. So that's something you decide. If you decide that, and you know what, we really can't make a type 1 error, you would choose a smaller alpha, closer to 0, but you can't choose 0 exactly. Otherwise, you will never be running a true hypothesis test that has any chance of rejecting the null. Now, computing the test statistic, that's something that you're going to have to do. It is going to be a z-test statistic. This is kind of the meat and potatoes. This is the calculation that you actually have to make here, where p hat is the sample proportion. P0 is what you're assuming the proportion to be from your hypotheses. And then you make this nice big calculation. You might remember we made a very similar calculation to this in chapter 8. And that is no coincidence. That is no coincidence. This formula is provided to you on the final exam in your formula chart. So that is great. You can keep that in mind. This general formulation of a hypothesis test is not provided to you. You have to know what you're doing and how to build up your hypothesis test when you come in to take the actual exam. So keep that in mind. But the actual test statistic formula is given to you. You're going to determine something called a critical value. This is going to be a z-score, or in a two-tailed test, it's going to be two different z-scores. And here's what you're going to do. It's kind of weird. In a two-tailed test, you're going to use your alpha. Let me zoom in on this. You're going to use your alpha. This is z alpha over 2 to determine the z-score on both sides, so that the critical region in total is alpha. The area under the curve outside these z-scores is equal to alpha. And if you end up with a test statistic that's in the critical region, you're going to reject the null hypothesis. If you end up with a test statistic that is not in the critical region, that's in this middle part, you're going to fail to reject the null hypothesis. And then after that, it just depends. If you're doing a left-tailed test, your critical value, your z-score, is basically going to be the smallest test statistic where you will still fail to reject the null hypothesis. Any smaller than that test statistic, and you're going to reject. You find that by making your critical region, the area under the curve, equal to alpha. And then for a right-tailed test, but then it has, on a left-tailed test, it has to be to the left. On a right-tailed test, it has to be area to the right. We will work several examples of this. I know this looks confusing at the get-go, but I will show you some very explicit examples of this stuff. So if your test statistic that you calculate falls within the critical region, we will reject the null hypothesis. If it does not fall within the critical region, we will not reject the null hypothesis. Now, we have to do some, these are called sometimes the success failure condition, to test a hypothesis regarding the population proportion. You need to make sure that your sample is obtained by simple random sampling. You remember, you also need to decide if n times p times 1 minus p is greater than or equal to 10. You also need to decide if your sample size is less than 5% of the population size. But that's usually going to be the case. If it's not the case, you can't really run a hypothesis test here using simple methods. You'd have to use something that's considered beyond the scope of this course. Okay, so let's actually run a hypothesis test for a population proportion. Let's see what it actually looks like. In 2001, 23% of American university undergraduate students had at least one tattoo. A health practitioner suspects that the percent has changed since then. She obtains a random sample of 1,025 undergrads and finds that 255 have at least one tattoo. Is this sufficient evidence to conclude that the proportion is different from the 0.23 at an alpha of 0.05, a significance level of 0.05? Use the classical approach. Okay, so we're going to work this one totally together. First of all, the null hypothesis, we're talking about a proportion. The null hypothesis is going to be that the true proportion of these students that have a tattoo is 0.23, that 23% of them have at least one tattoo. Now she's testing whether or not this proportion is different from 0.23. So she's testing that it's not equal to 0.23. Let me draw a little slash through it. Boom. Thus, this is a two-tailed test, simply because the alternative hypothesis is the not equal to. I will remind you that, boom, look at the two-tailed test. Here, the P0 is the 0.23, the value from the hypotheses. So this is a two-tailed test. Let's go back in time and put it where it belongs. We're actually going to need a little more space than this, it looks like. Yada, yada, yada. And then our slash. So it's a two-tailed test. So alpha is going to be equal to 0.05. That's our probability of making a type 1 error. That's going to be the level of the test. Now, we're going to look at this thing and what we want is that alpha is going to be the area under the curve found here or here. Together, these two areas should be 5% or 0.05, which is our alpha. But you got to split that in half. So we're going to say, that's an arrow, we're going to say 0.025 lives in there and 0.025 lives here. So our critical z-scores, we need to go to our z-chart and we need to find z-scores that where the lower z-score has 0.025 to the left of it, the upper z-score has 0.025 to the right of it. So let me pull up a z-chart. We're going to find that's going to be negative 1.96 and positive 1.96. But don't believe me, let me bring up this z-chart here, and I will show you that this is stuff we've been working on already this semester. Give me a moment to get it loaded. had it open, but it decided to close on me. Because sometimes technology just likes to not work. Not all the time, but sometimes. Okay. So what we need to find is we need this area to the left to be 0.025. So we look inside the chart, we look for 0.025 or as close as we can get to it. And hot dog, we are in luck because here's 0.025 exactly. And that corresponds to a z-score of negative 1.96. So back to it once more, unto the breach. Unfortunately, it cleared stuff out. But anyways, so this z-score is going to be negative 1.96. This z-score will be positive 1.96. So if we calculate a test statistic and it falls down here, it is less than negative 1.96 or greater than positive 1.96, we will be rejecting the null hypothesis. That's called our rejection region. Remember, we're testing that p is equal to 0.23 or p is not equal to 0.23. Our alpha is 0.05. Our procedure is going to be if our test statistic is less than negative 1.96 or greater than positive 1.96, we reject the null. Otherwise, we don't. We don't reject the null. Now we need to calculate the test statistic. We need to know what p hat is going to be. That's going to be the sample proportion. The researcher went out, sampled 1,025 undergraduates, and found that 255 had at least one tattoo. So the sample proportion is going to be 255 out of 1,025 total. And we can use a calculator to simplify that. .249. We'll round to 3 decimal places. So it would appear that the sample proportion is 0.249. So that's not equal, that's not exactly 0.23, but we can't reject based on that. We need it to be a good distance from 0.23. We need it to be quite a number of standard deviations away from it for us to reject. So our test statistic value, we're going to take p hat, which is 0.249, minus p0, which is the assumed value of the proportion from the test, from the null hypothesis. So minus 0.23, all divided by the square root of 0.23 times 1 minus 0.23 all over n, our sample size, which again was 1025. And once we calculate this test statistic, we will have a lot of our answer. So give me a moment, I'll calculate it. We're going to get a test statistic value of 1.45. So we got 1.45, but if our test statistic is less than negative 1.96 or greater than positive 1.96, which it's not, we reject the null. Otherwise, we don't. So we are not rejecting the null. We only reject the null hypothesis if the test statistic turned out to be quite extreme, if it was extreme or very far from zero, but it wasn't here. It was well within these two values. This is called the fail to reject region. So that's going to be an issue here. Our test statistic was 1.45. Our critical values were negative 1.96 and positive 1.96. Oops. So our test statistic was not less than negative 1.696 nor greater than positive 1.96. So we failed to reject the null hypothesis. And when we fail to reject, we're saying there's not sufficient evidence to conclude that the proportion of undergraduates who have at least one tattoo is different from 0.23. That's the bottom line. If we had rejected the null hypothesis, we would be saying there is sufficient evidence. But since we are not rejecting, we're saying there is not significant evidence or sufficient evidence. So what we really talk about, we talk about the idea of something being statistically significant. And what that really means in brass tacks is that something is either likely or unlikely. In this case, if we were to reject the null hypothesis, we're saying that it's unlikely that the null hypothesis is true. So there's a couple things you can do. Maybe they're not super interesting. But what we're going to say is that we don't come out and say, oh, this is definitely the case. Oh, this is 100% the case that the null hypothesis is false. No, we use a little bit more of a safe approach and we say it's statistically significant. If we're going to reject the null hypothesis, we're going to say our evidence is statistically significant. If we fail to reject the null, we're going to say our evidence is not statistically significant. So we're not going to go super into this part here. Finally, our next approach is going to be something called the p-value approach. We'll end with this little blurb here. This measures the probability that your sample is compatible with the null hypothesis. That's a good way to put it. So basically, the p-value is like saying, hey, is your null hypothesis likely, or rather, it's not quite that. The p-value is a little bit hard to explain, but it's going to be a probability between 0 and 1. The higher the p-value, the closer it is to 1, that actually is very favorable with the null hypothesis. So we're going to calculate a p-value. If your p-value is large, we're going to say, actually, that is on team null hypothesis. So we are going to fail to reject the null hypothesis. We're not going to reject it when you have a large p-value. However, if your p-value is small, remember the p-value is like your compatibility with the null hypothesis. If the p-value is small, that is shedding some doubt on the null hypothesis. How do we decide if a p-value is small enough so that we will end up rejecting the null? If the p-value is less than alpha, if the p-value is less than the significance of your test. That's the brass tacks. If the p-value is less than the significance of the test, reject the null hypothesis. Otherwise, don't reject. It's that simple. A good little way to remember that is this cute little rhyming statement. If the p-value is low, the null must go. So a small p-value favors rejection. It says 0.05 is typically the cutoff. Well, it's really just whatever alpha is. And alpha, we usually pick an alpha of 0.05. Not always, but we can. So a small p-value was going to lead us towards rejecting the null hypothesis. A large p-value, a p-value that's greater than our alpha, is going to lead us to fail to reject the null hypothesis. So just some interesting ideas here. We will pick up on these ideas next time.